Back, everybody. AP Chemistry, Unit 1, Section 3, taking a look at the trends that the periodic table will suggest for different traits along the way for different atoms. And so one of the periodicity traits that we will be taking a look at first is going to be the size of the atoms, okay? What we refer to as the atomic radii. Now remember, in the core, we have the protons and neutrons, as I've said exhaustively throughout this chapter. We find the protons and neutrons in the core, and on the outside, giving the true size of this, are going to be the electrons, okay? And the question is, how big are these atoms? And as we can see from the table, if we just follow straight across, there's a couple different trends that we find. The trend that we see, first of all, the easy trend to find as we look at periodic table, energy level 1, energy level 2, 3, 4, 5, 6, and 7. Remember, these guys are up in here. As we go down, we see obviously that those are going to get bigger because we have our nucleus and we have energy level 1, energy level 2, energy level 3, and so on. Obviously, that's going to get bigger as we go down. But the question is, why do we find as we go across the period, from lithium over to neon, why do we find that that atom is actually getting smaller? That's odd, because if I see that I have one proton in S, then two protons in S, three protons in S, and we're adding subsequent electrons to that, if we're adding to there, you would think that those would be getting bigger. However, the opposite is true. They're going to be getting smaller. Now, the answer to that is actually quite simple, and we use Coulomb's law to explain it. Now, Coulomb's law, kind of a weird set of I guess, factors here within it, that UE stands for the forces between the particles. And so the question is, what do we mean by that? Well, here are the different charged particles, okay? Protons and electrons are the particles themselves. So if I look at the forces between those particles as a function of their distance, okay? So the question is the distance portion as well. Well, notice that the force is that when we look going across, if I go through and say we have one proton, another proton, another proton, we're adding electrons, we multiply that in there, so my force gets bigger. What do protons and electrons do? They attract one another. Opposites will attract with that. And so what happens is that magnet, if you will, of that core gets stronger and stronger and stronger, and that pulls the electrons in closer and closer and closer. So the result is that the atom actually gets smaller as you progress across the period. Now, using the same concept of Coulomb's law, as we go down, I just said we'd add an energy level. So visually, that just makes sense. But what's happening? The distance is getting greater. When we divide by a larger number, we end up with a smaller integer, don't we? And so we can answer the question of going down the periods as well. It's going to be getting a larger atom because the force pulling those electrons is less and less as we go. Think about it in terms of forces. We refer to that force as the effective nuclear charge, the pull created by the protons within that nucleus. Okay, think about it. I used the phrase just a bit ago talking about a magnet. Okay, so if it's a larger Q, a larger force, that's going to be pulling it in, the stronger the force, and that's going to be pulling it in, resulting in a smaller atomic radius. If it's a weaker force, then all of a sudden that attracting force is less, and so the electrons go further out. So if we take a look at the size of those ions in there, and atoms as they are, compared to the atoms, I should say, we take a look at it this way, and we see that the chlorine atom itself is going to be a little bit different than the chlorine ion. We did that in the last section, okay, the electron configurations. So we see it is still chlorine, and chlorine has atomic number 17, meaning that it is 17 total protons. Well, we have 17 protons in both cases, don't we? But here we have 17 electrons, and here we have 18 electrons. So what happens? The atom itself is smaller than the ion because we have one more electron, and we find we have more of that second second total force that's involved there. And so the attracting force is going to be less because we have more electrons. The ion is going to be larger than the atom. Now let's take a look at another situation. That's anions. Let's take a look at cations. And so we can compare with calcium and the calcium ion. Now once again, calcium is atomic number 20. We have 20 total protons in both cases. But we have 20 protons pulling against 20 electrons versus 20 protons pulling 18 electrons, because this is a +2 charge. Okay, so we have a +2 charge in there, lost 2 electrons along the way, we can see. So there's 20 protons pulling against only 18 electrons, holding them much closer. Okay, so that's kind of how that works. If we take a look at comparing the calcium ions versus our chloride ions. Now, let's take a look at some other examples, and that might be comparing the sodium. In fact, let me clear this all out. Let's compare sodium now to another atom of argon. All right, so here's my sodium, and here's going to be my argon. Notice that we're in the same area, aren't we? And so we see sodium has 11 total protons, and it has an electron configuration of 1s2, 2s2, 2p6, and 3s1. All right, if we're comparing forces, argon has 18 protons, and it has 1s2, 2s2, 2p6, 3s2, 3p6. All right, so if I was going to be comparing these together, I have 11 protons, and I am pulling 11 electrons. Okay, I have 18 protons pulling 18 electrons. And so my attractive force is stronger here. And so that means that my atom is going to be smaller. And so my sodium atom is going to be a larger size, a larger diameter than my argon would be. Okay, got to flip the thinking a little bit, and then we take a look at comparing fluorine with iodine. Okay, so my fluorine is right here, my iodine is right here. All right, 1s2, 2s2, 2p5, and then 1s2, 2s2, 2p6, 3s2. You get the idea, all the way up to 5p5. Okay. So there's going to be 53 total protons versus 9 total protons. Okay, taking a look at those, plug the numbers in. We see the distance that they have to go is quite considerably larger. So my atom of fluorine is going to be considerably smaller than my iodine. Okay, because there are more shells, there's less force. Okay, my iodine is going to be the larger of the atoms. Pretty straightforward. I don't think you'll have too many problems with that one. Now, next up, first ionization energy. Think of it in terms of the convincing it takes to get rid of electrons. Now we have to remember one of the basic trends. As we go to the right, remember, these will form negative ions. These will form positive ions on this side as we go to the left. So if they're forming negative ions, they tend to take in more electrons to get to that stable octet. It would take a lot of convincing to give up electrons, wouldn't it? And so seeing the first ionization energy, it takes more convincing to give up electrons. Okay, if that's what the definition, it takes more convincing, more energy to give up electrons as we go this way. Now as we go down, remember those electrons are way out here. And so as we add electrons going down, we find electrons, this distance is so far. Remember that force that we were talking about, that force pulling in, that force diminishes as we go further out, and so it doesn't take as much convincing. It decreases as we go down. Okay, so pretty straightforward concepts. I'm just keeping in mind the applications with those. Okay, that's the first ionization energy. Now, other way to think of things in terms of periodicity is electronegativity. The force it exerts to take in electrons, how much they like to take them in. Bad way to describe it when you say they don't like to do anything, so be careful with that. But how much do they have an affiliation? An electronegativity is actually a number. And if you remember from previous lectures, we use that to figure out polarities as well, the electronegativity difference and so on. So the idea is how much they like to take them in, the attractive force to take in electrons, and as it follows the same trend that we found with ionization energy. So as we go to the right, that force will be increasing, and as we go down, it decreases. Now this is what we use to factor in the percent ionic character. Okay, the percent ionic character is how much it will form an ionic compound versus a molecular compound. So the percent ionic character is telling me what type of bond we're going to be getting. And so we take our big number, whichever that is, it might be a value of 0.9, it might be a 1.5 or whatever. We take our big number minus our small number, okay? So this is whatever the big number is, so we'll never have a negative value. I guess is the point of what I'm trying to say. Small value here. And we're going to divide that by that first big number times 100%. That's going to give us our ionic character. And so if it is an ionic compound, when we form a bond between these elements, if we have an ionic bond, I know that the general rule of thumb is if it involves a metal of some type, but the reality is it has to do with the percent ionic character. If it involves an ionic bond, remember we are transferring electrons. And if that ionic character is between 50 to 100%, if that difference is between 50 and 100%, that is going to form an ionic bond. So let's take a look at an example of a bond between potassium and chlorine. Okay, the large value on chlorine is going to be a 3.0. The small value is going to be potassium, that's a 0.8. So we're going to divide that by our 3.0 times 100%. Okay, that gives me a value, a percent ionic character of 73.3%. Okay, that tells me that chlorine is pulling with that much force. Okay, so it's taking the electron away from the potassium and putting it into that octet. Okay, so I know that that's going to be an ionic bond. Now, let's take a look and apply this to covalent bonds. Okay, a covalent bond, again, dealing with our percent ionic character. Let's take a look at covalent, where they're going to be sharing electrons. That value is going to be anywhere between 0 and 50%. Okay, so let's take a look at the situation between hydrogen and oxygen. All right, just eyeballing it, I see hydrogen right here, I see oxygen here. My larger value is a 3.5 minus our 2.1 divided by my larger value times 100%. And so I use my electronegativity to calculate my percent ionic character. I see that this ends up being a 40%. Therefore, it is covalent. Okay, and I can actually figure out if that's going to be polar or nonpolar from that as well. Now, what's happening in these cases, if I go back to the KCl and the water example, because I have one hydrogen to an oxygen, we can do that. Here's what's happening. If I look at a orbital diagram, okay, here's potassium. I'm not going to do the 1s1, 2s2 and all that. It ends with a 4s1. Okay, I take a look at chlorine, and that ends with a 3s2 and a 3p3. 5. If I look at these orbitals, 1, 2, 3, here's 1, 2, 3, 4, 5. Here's my 1s1. What's going to happen is, to form a bond, the chlorine is actually going to strip off the electron and put it right here. Okay? Now what's happening in the case of water when it's covalent, hydrogen is here. Okay? Now we have water, so there's actually 2 hydrogens involved. That's a 1s1, 1s1. So there's 1 electron here, there's 1 electron here. And then we have oxygen, and that has a 2s2 and a 2p4. 1, 2, 3. Here's 1, here's 2, here's 3, and here's 4. Now, what's happening in this case, if it is covalent, this electron is going to go down here, and this electron is going to go up here. However, at the same time, this electron is going to go down here and fill that 1s, and at the same time, this electron is to go up here and fill that s. So they are trading back and forth to make a covalent bond, and that's what that means. Okay? So calculating out and then diagramming out what's going on are 2 separate skills, but periodicity, pretty straightforward. I don't think you'll have any problems just using some of those equations. Now, we're going to have a photoelectric spectrum quiz. We have some NIMSY problems to be reviewing and review multiple choice problems, and that will be wrapping up the entire chapter to get ready for our first big test in Unit 1. I think you have a lot of success with it if you know how to work your calculations, and I wish you luck.